Hey everyone, if you're studying Object-Oriented Programming, or OOP, you probably already know it's all about modeling your code based on real-world objects. Sounds simple enough, right? But there are a few theoretical concepts that consistently trip up even the absolute best students. Well, today, we are going to completely leave that complexity behind. In this explainer, we're going to demystify one of the most strategic and, honestly, most misunderstood principles of OOP, abstraction. By the time we're done here, you are going to be fully prepared to ace those tricky exam questions and totally nail your next technical interview.
Imagine you're sitting in your final exam, and your professor asks you to evaluate this single simple line of code. You're trying to create a new object from an abstract class called shape. Why is this going to instantly fail and throw a massive error? This right here is a classic professor trap. It targets a fundamental misunderstanding of what abstraction actually does in our code. Keep this question in the back of your mind, because we're about to build the exact knowledge you need to answer it with total confidence.
Okay, here's our game plan for today. 1. What is abstraction? 2. Abstract classes. 3. Interfaces. 4. Abstraction versus encapsulation. And 5. The final test. Let's jump right in.
Section 1. What is abstraction? Hiding the how to show the what.
So, the formal definition of abstraction is hiding unnecessary internal complexity and details from the user and exposing only the essential functionalities. Basically, it's creating a black box. When you use a really complex system, you don't actually want to be burdened with knowing exactly how all the tiny gears are turning inside, right? You just want to know what the system can do for you. You care about the inputs and the outputs, and you let the system handle all the messy details internally. Think about driving a car. When you get in, you see a steering wheel, a brake, and a gas pedal. You press the gas pedal and the car accelerates. You don't need to understand the precise mechanics of the internal combustion engine or the fuel injection system or exactly how the spark plugs ignite the gas. The car's complex internal workings are completely hidden from you. You're just given a simple abstracted interface, the pedal, to interact with. Well, in programming, abstraction does the exact same thing for our users and for our fellow developers.
Moving on to Section 2. Abstract classes, the blueprint.
Think of an abstract class as a blueprint. It's basically a template that contains incomplete methods. Methods that say what should happen, but they don't actually provide the code for how it happens. And because it's incomplete, you cannot instantiate it. You literally cannot create a direct object from an abstract class. And right there, that's the answer to our hook question. You can never say shape equals shape if shape is abstract. It's just a blueprint. In contrast, concrete classes are the child classes that inherit from that abstract class, fill in all the missing code, and can actually be instantiated into real objects.
Let's look at a highly typical exam question derived straight from our source material. You're asked to calculate the area using an abstract class called shape and a concrete child class called circle. The circle has a radius of 5. So, how does abstraction actually solve this? Let's break it down.
Here is exactly how a tutor would build this out. Step 1. We define our abstract shape class. Inside it, we create an abstract method called area. Now, we don't write any math here. We just leave it empty. We're simply saying, hey, any shape that exists must be able to calculate its area. Step 2. We create our circle class, and it inherits from shape. Step 3. Because circle is a concrete shape, it is legally forced to override that abstract area method. It provides the actual formula, 3.14 times the radius squared. Notice how we've successfully hidden the general concept in the parent class and put all the specific, messy details in the child class.
So if we run our code and pass in a radius of 5, the math is 3.14 times 5 squared, which is 3.14 times 25. The final output is 78.5. If you write this logic out clearly, step by step, you are going to get full marks on that question, for sure.
Section 3. Interfaces, the strict contract.
Our sources give us a really clear rule here. An interface is a pure contract. It only contains method signatures with no implementation. While an abstract class might give you a mix of some normal methods with code and some empty abstract methods, an interface is 100% empty. It is purely a list of rules. It says, if you want to be part of my system, you absolutely must possess these specific behaviors.
So when you're sitting in your exam, how do you know which one to use? Here's the trick. Use an abstract class when you want to share some common already written code among child classes, but you want to leave a few specific methods blank.
And remember, in most languages, a child can only inherit from one parent abstract class. On the flip side, use an interface when you only want to define a strict behavioral contract without sharing any pre-written code at all. The true beauty of interfaces is that a single class can sign multiple contracts. It can implement multiple interfaces at the exact same time.
Section 4. Abstraction versus Encapsulation, the ultimate trap.
Now, what's really interesting about this concept is the difference between design and security. Abstraction is a design-level concept. It hides complexity to simplify the system for the user. It focuses entirely on what the object can do. Encapsulation, however, is a security-level concept. It hides your raw data to protect it from being messed with from the outside. It focuses on how the data is managed and protected.
Let's make this totally concrete with an example right from our source documents. If you have a bank application, you definitely don't want anyone to directly change the balance variable. So you make the balance private, and you force people to use safe deposit or withdraw methods. That is encapsulation, protecting your data. On the other hand, let's say your app accepts credit cards, PayPal, and crypto. You create a standard pay method interface, so the checkout button just clicks pay without caring how the specific bank routes the money. That is abstraction, simplifying the complexity. So the absolutely crucial point to remember for your exam is that they work perfectly together, but they are absolutely not the same thing.
And that brings us to Section 5, the final test, putting it all together. All right, here's your final challenge to see if this all clicked. We have an abstract animal class. Inside it, there's an abstract method called sound calling. We create a concrete dog class that inherits from animal, but the programmer makes a mistake and completely forgets to write a specific sound calling method inside the dog class. They try to run the code. What actually happens? It totally crashes. You get a massive error. This is the strict rule of abstraction in action. An abstract class is a mandatory contract. If a parent says all animals must make a sound, the child class absolutely must override and implement that method. If you leave it out, the compiler will just refuse to run your code. It's essentially a built-in safety net to ensure your software is designed perfectly.
Let's quickly lock this all in with a rapid-fire cheat sheet of our main takeaways. Number 1, abstraction hides the how, so you only have to interact with the what. Number 2, abstract classes provide templates that literally cannot be directly instantiated. Number 3, interfaces provide 100% strict behavioral contracts with zero implementation. And finally, number 4, please do not confuse abstraction with encapsulation. Encapsulation protects your variables. Abstraction simplifies your system's complexity.
And there you have it. You have fully conquered the theory and the application of OOP abstraction, and you are more than ready to face those tricky exam questions head-on. Now that you know how to hide the complex, messy gears of your code behind clean, simple interfaces, what massive system are you going to abstract and simplify next? Keep coding cleanly, and I'll see you in the next explainer.